Hello, everyone. Welcome to a new lecture of our course on processing in memory systems. Today, I'm going to briefly present our work SParse-P towards efficient sparse matrix spectral multiplication on real processing in memory architectures. This work was led by Cristina Genola as part of her PhD thesis when she was at the National Technical University of Athens. Now she's working as a postdoc at the University of Toronto. Let's start with a little bit of summary. Our work is about efficient algorithmic designs, and it presents the first open source implementation of a sparse matrix vector multiplication in form of a library that is called SParse-P for processing in memory systems. As you can see on the slide, SParse-P is open source. In this work, we perform an extensive characterization. It's the first comprehensive analysis of SpMV on a real processing in memory architecture. Here in this presentation, I'm just going to show a little bit of the results that we include in longer presentations of this work and, of course, in the paper. Sparse matrix vector multiplication is a good candidate for processing in memory because it's highly memory bound. If we analyze the sparse matrix vector multiplication with the roofline model, we will observe that it falls in the memory bound area of the roofline. So it's a good candidate for processing in memory systems. We are already familiar with processing in memory systems in this course and with real processing in memory systems that, as you can see on the slide, typically have a host processor that has access to a main memory, typically DDR DIMMs, and also a PIM-enabled memory that works as an external accelerator. Examples of that are the UPMEM PIM architecture or HBM PIM from Samsung or AIM from SK Hynix that we have previously presented in this course. SParse-P is an SpMV library for real processing in memory systems, and as you will see, SParse-P is composed of 25 SpMV kernels spanning different matrix formats like CSR, COO, BCSR, and BCOO, data types, different data partition techniques, different load balancing schemes, and also different synchronization approaches. We provide a comprehensive analysis of SpMV using 26 sparse matrices of different characteristics, and in our work, we also show a comparison to CPU and GPU systems, as well as recommendations for software designers and for hardware and architecture designers of future PIM systems. Let's start with a little bit of the description of these SpMV kernels for real PIM systems. If we want to execute SpMV on a real PIM system, we'll first have to load the matrix, but then we'll have to load the input vector from the main memory to the PIM-enabled memory. Then we will execute the kernel, the SpMV kernel in the PIM-enabled memory, and finally we will retrieve partial results to the host CPU. That might need to merge these partial results. In terms of how to divide the workload over the different cores, different PIM cores, or different DPUs in the case of the UPMEM-based PIM system, we can do it in different ways. We can apply 1D partitioning techniques. In this case, we are dividing the matrix in multiple rows, and different rows, different chunks of rows are assigned to different PIM cores, or we can do a 2D partitioning where each core is going to receive part of a row and part, so multiple columns of partial rows, basically. There are trade-offs here, because in the case of the 1D partitioning, we perform the complete SpMV computation only on the PIM cores, and this way the processor, the host processor, can just retrieve the output vector, but 1D partitioning implies that we need to replicate the input vector as many times as DPUs or PIM cores we have in the system. However, in 2D partitioning, because we are partitioning the rows, we can also partition the input vectors, and in this case, we don't need to transfer so much of input vectors to the PIM core. So here we are trading off computation versus data transfer cost. For the 1D partitioning technique, as you will see in the longer version of this lecture and in the paper, we have used load balancing approaches for CSR and for COO format, and also for BCSR and BCOO formats. These approaches try to balance either the rows or the blocks, or either the non-zero elements. In the case of CSR or BCSR, partitioning non-zero elements is not that easy because we need to do it at either row granularity or block row granularity. That will still imply a little bit of imbalance between the different PIM cores. Here we can see an example of 1D partitioning with load balancing of non-zero elements. As I said, for CSR, we are doing it at the row granularity. And even though here we are trying to balance the number of non-zero elements the best we can for the different cores, but still we need to do it at a row granularity. However, in the case of COO, we can partition at the granularity of a single element or a single non-zero element. So that's the key difference here. In 2D partitioning techniques, there are different ways of doing 2D partitioning. For example, we can use equally sized tiles. In this case, there is a high non-zero or might be high non-zero imbalance across PIM cores, or we can use equally wide tiles. In this case, there is high non-zero balance across PIM cores in the same vertical partition, but there might not be non-zero element balance in different vertical partitions. And finally, we have the variable size tiles. In this case, high non-zero element balance across all PIM cores. Now, if we take a look at how to load balance inside the PIM cores across threads, it's kind of similar as well. In the multi-thread PIM cores, if we use 1D partitioning, we can balance rows, or we can also balance non-zero elements. So we also explore in this work various load balance schemes across the threads, and also various synchronization approaches among PIM threads. And here you can see the different synchronization approaches that we have used. Coarse grain approach, where we are using a single mutex for the entire output vector, or fine grain approach, or fine grain locking approach, where we have multiple mutexes to access the output vector, and finally the lock-free approach, in which we avoid the use of mutex by having individual threads, for example, thread 1 in this example, merging partial results and writing to the output vector. So in total, as I said earlier, the SpMV library contains 25 SpMV kernels. As you see, there are different partitioning techniques for 1D kernels, equally sized or equally wide or variable size tiles of 2D partitioning, different matrix formats, basically CSR, COO, BCSR, and BCOO, different load balance among PIM cores and PIM threads, and synchronization mechanisms, and also data types. We can very briefly take a look at some of the key takeaways of our study. In this work, we use a real PIM system from AppMem with more than 2,500 PIM cores. Remember that this PIM system has a main memory and that can be accessed by the host processor, as well as the PIM-enabled memory with a maximum of 160 gigabytes of PIM-enabled memory. And inside each of the DIMMs, we have 16 chips typically. Inside each PIM chip, there are 8 DRAM banks of size 64 megabytes. And next to each DRAM bank, there is a PIM core called DPU in AppMem terminology. That is a pipeline fine-grained multi-threaded core with its own SRAM-based instruction memory and SRAM-based scratchpad memory of a size 64 kilobytes. For the experiments, we have used matrices, 25 sparse matrices from a well-known and public collection of sparse matrices, including different sparsity patterns and variability in the regular patterns, and also in the block patterns. There are regular matrices, and there are more scale-free matrices following a power law distribution, and each of them provide different insights. We did a lot of analysis. For example, inside a PIM core, we analyzed the scalability for different numbers of PIM threads. The general observation here is that scalability increases up to 16 threads, but this is because in these experiments we use 4, 8, 16, or 24 threads. So performance saturated at 16 threads, because in the AppMem DPUs, the AppMem PIM cores, we know that performance saturates at 11 threads, 11 PIM threads. So the next number that we tested here is 16. So that's why it's where we normally see the performance saturation point for these kernels. When executing the kernel on multiple PIM cores, there are also some interesting observations that you can check in our paper. Here you see that some results, speed up results for 2D equally wide tiles and 2D variable size tiles, both regular matrices and scale-free matrices. And the general observation is that COO and BCO formats provide higher non-zero element balance across PIM cores and PIM threads than CSR and BCSR respectively, and this translates to significant performance improvement, significant speedups of COO and BCO over CSR and BCSR. So one key takeaway of our work is that the compressed matrix format that it's used to store the input matrix determines the data partitioning across DRAM banks of the PIM-enabled memory. And as a result, it affects the load balance across PIM cores and the threads inside the same PIM core with the corresponding performance implications. So ideally, we should design compressed data structures that can be effectively partitioned across DRAM banks in order to provide high computation balance. That would be the recommendation for an ideal or better suited compression scheme for matrices on PIM systems. Now we can take also a look at the end-to-end performance, just to show you some results, scalability results with different number of cores from the PIM cores from 256 to 2048. For example, for 1D partitioning, what we see is that the scalability is limited by the load time. And the reason is that we have to broadcast the same input vector to all PIM cores. So the more PIM cores we have, the more data transfers we will have. And in the end, this limits the scalability of the end-to-end performance. So in 1D partitioning, the number of bytes to load the input vector to the PIM cores grows linearly with the number of PIM cores, and in the end, this affects the scalability. So there are better choices, as we can see in this slide. 2D partitioning in the end reduces a lot the load time and makes it more suitable in the majority of cases for this kind of PIM system. So key takeaway number 4, the 1D partition kernels are severely bottlenecked by the high data transfer cost to broadcast the whole input vector into the DRAM bank of all PIM cores. So one recommendation is to, if we really want to use a 1D partitioning technique, would be to optimize the broadcast collective in data transfers to have more efficient copies of the input data to the DRAM banks in the PIM system. We also analyze the performance of SpMV in comparison, the Sparse kernels in comparison to CPU and GPU. And there are some important observations here. We can call CPU and GPU as processor-centric systems because they have a memory that is passive, and we need to move all the data that we want to process from the memory to the processor. These processors are very powerful in terms of peak performance, but they are not that great in terms of memory bandwidth, as we can see on the table. However, on a PIM system, which is a memory-centric system, compute units might not be so powerful. Observe that the peak performance is significantly lower than on the CPU and the GPU. However, the bandwidth is usually much higher, as we can see here. And when we compare only the kernels, in this case, we have a comparison for CO compression format using 1D partitioning in the case of the PIM system for 32-bit floating point numbers. One is an interesting observation here is that the PIM system achieves a significantly higher fraction of the peak performance, more than 50% of the peak performance, significantly higher fraction than that of the CPU and the GPU, which, as you see, are less than 1% of the peak performance, what they are leveraging when computing SpMV. And this shows that CPUs and GPUs are way imbalanced in terms of the ratio between peak performance and memory bandwidth. And they are clearly not suitable for, or not so well designed for, these kind of workloads. In a PIM system, even if the overall performance might not be that high in some of the cases, but at least we can see that peak performance and bandwidth are much better balanced for workloads like SpMV. We also perform a comparison, an end-to-end comparison, including the data transfers. In this case, we can see, because we are only doing one SpMV that requires input transfers and output transfers. Here we see that the overall performance is better for the CPU, basically because it doesn't need to have to do data transfers, as is the case of the GPU or the PIM system. We also perform a comparison in terms of energy, and we observe that even though the most energy efficient device is the GPU, but the PIM system is like 1.38 times higher energy efficiency than the CPU. You can find many more results in the paper. In conclusion, SpMV is as a fundamental linear algebra kernel for important applications in HPC, machine learning, graph analytics, etc. It's highly memory bound in conventional processor-centric systems, and processing in memory systems can tackle these data movement bottleneck. Key contributions of our work are Sparse, which is the first open source SpMV library for real PIM systems with a comprehensive characterization and analysis of the SpMV on a real processing in memory systems, and multiple recommendations to improve hardware and software in the future. This is the paper. You can find links to the paper that was published at Sigmetrics 2022, also the archive version, and the source code in our repository, as you can see. For many more details about this lecture, you can check this previous lecture that was delivered by Christina herself, where she provides many more details about the implementations, and especially about the evaluation, including takeaways and recommendations. This is all for today. I hope that you found this lecture interesting, and take a look at the paper and the longer version of this lecture. Thank you very much for your attention, and see you in the next lecture of our PIM course.